Hey, here we go. So I'm going to start off with cosine t, right? So here we've got the t-axis, and here we've got the y-axis, okay? It's not the f of t-axis or the f of x-axis this time, because if I called it f of x or f of t, I would be confusing myself. So I'm going to call this the y-axis, and I'm going to call this the t-axis. Now, this function is y equals cosine t. In fact, I'm going to put some y's in here for us. Here's a y. This is y equals cosine t. Now, here's the function here, all right? And there it is. It's your standard cosine. Now, I'm going to define a new function with a variable x, okay? And it's equal to the integral, or the area under the cosine t function, where the upper and lower bounds are not set. So they're not numerically set. For example, like this would be like 1, and this would be like 2, but it's actually a variable. So in a way, I'm defining an area where not like the function itself varies, but I'm defining an area where the endpoints or the upper and lower bounds of the area varies. So imagine these dotted lines being able to kind of slide back and forth based on my choice of x. And as a result, I define various areas based on my choice of x. All right. So now that you hopefully have that sort of imagined in your mind, now a very common question would be for a calculus teacher to ask you to take the derivative of that area, right? And you say, well, okay, well, what's the rate of change of this area as the x value changes? So if I increase the x value or decrease it, what happens to this area? Does it increase? Does it decrease? And so forth like that, okay? And so a lot of people would say, well, let's use the second fundamental theorem of calculus with this. Well, I'm going to kind of ignore that for now. And I'm just going to actually just sort of say, look, I'm going to take the I'm going to take the integral of cosine t. Well, the integral of cosine t is sine t, and I'm going to evaluate it at the upper and lower bounds here, okay? And then, when I evaluate an integral at the upper and lower bounds, I just take the integrated value here, so sine, and I place the lower bound and I place the upper bound in their appropriate locations, and I find the difference. But I still haven't noticed. I kind of ignored the derivative here for the time being, because the derivative of f of x is f prime of x, or I could write it as dx. So I ignored that for the moment. But now that I've taken the integral over here, I'm going to go ahead and address the fact that I have a derivative written here. So I'm going to apply the derivative to this integral, or the resultant integral that I've already integrated here. And now look, d dx is just the derivative of this thing with respect to x. And now I've got x's in there, so it's pretty cool, and it's a pretty easy thing to do, is to take the derivative of sine x squared minus 1 is cosine x squared minus 1 times the derivative of x squared. So I'm just going to use the chain rule here. And the derivative of sine x is cosine x. The negative stays there. But now if you look close, and this is the answer, right? And so, but it turns out if you do it this way, you can go ahead and do it this way, but you can actually skip all the way to the end by, look, I've got a cosine in both cases. So in the end, I integrated and then differentiated. So I just get back what I started with. And all you have to do is you have to take your endpoints, your upper and lower bounds. Your upper bound goes here, your lower bound goes there. You put a minus sign in there, but don't forget, you always have to do the derivative of your upper bound, and then you would multiply it by the derivative of your lower bound here too, if you had one. But it turns out the derivative of x is just 1, so I can write that there. Anyway, so there's the solution. You actually can just skip straight to there. And if you did, what you're doing is you're kind of using what's called the second fundamental theorem of calculus.